Good morning. We're going to take a look at exponential functions today and how to graph them. Okay, so first, just want to talk to you about what they look like. Exponential functions mean the x is in the exponent. When you graph them, they look like this. F of x equals b of x. It's called an exponential function if b is greater than 0, b is not 1, and x is a real number. So all of these are going to be bigger than 0 numbers for the b, not negative. And so these are all going to represent exponential growth and exponential decay. Okay, what happens when you graph these functions? All right, well, here's a couple examples. 3 of x, 3 to the x power, 5 to the x power, 1/2 x. Whenever you graph them, all of these things happen. They're 1 to 1. The y-intercept is 0, 1. They have no x-intercept. The domain is all real numbers, and the range is 0 to 1. And I'll show you that right now when we graph one of these. So in order to graph them, it's probably helpful to fill out a chart based on the info. So here we have the equation f of x is 2 to the x power. So imagine plugging in these numbers into the exponent, and then let's see what we get. So if I plug a 0 into here, I get 2 to the 0 power, which is 1. If I plug a 1 in, I get 2 to the 1 power, which is 2. If I plug a 2 in, I get 2 squared. Oops, let me erase this. I get 2 squared, which is 4. 2 to the 3rd power is 8. 2 to the negative 1 power flips, so I get 1 over 2. And 2 to the negative 2 power would be 1 over 4. Okay. All right, let's keep going here. Let's see what happens when I plug this into 4. It's going to get some similar numbers here. 4 to the 0 power is 1. 4 to the 1 power is 4. 4 squared is 16. 4 cubed is 64. 4 to the negative 1 is 1 over 4. And 4 to the negative 2 will be 1 over 16. Okay? All right, now let's take these and try to graph them. Notice some of these things. When x is 0, y is 1. When x is 1, y is 2. And so we end up getting this exponential graph here. So when x is 0, y is 1. When x is 1, y is 2. Then we're going to square it, 4. We're going to keep going, okay? And then the opposite goes for this other one. Notice that the one that was 4 has a much higher graph. Just shoots up a little bit faster, okay? So the bigger the number, the quicker your graph goes up. The smaller the number, the more gradual it is, okay? All right, let's keep going here. Graph the exponential functions here. Now this time we have fractions in here. So let's see what happens when we graph fractions. If I do 1/2, why doesn't this want to work? 1/2 to the 0 power, that's 1. If I do 1/2 to the 1 power, that's 1/2. 1/2 to the 2nd power would be 1 over 4. I square it. 1/2 to the 3rd power would be 1 over 2 to the 3rd, which is 8. Now, if I do 1/2 to the negative 1 power, that switches this, flips it, so it becomes 2 over 1, so 2. And 1/2 to the negative 2nd power switches it and squares it, so it's going to become 4. Okay, let's repeat the same process for the 1/4. I have a feeling this one's going to be a more steeper curve. So when I plug in a 0 into here, I get 1/4. If I plug in a 1 into here, excuse me, let me fix that. If I plug in a 0, I get 1. If I plug in a 1, I get 1/4. If I plug in a 2, I get 1/16. If I plug in a 3, I get 1 over 4 to the third power, which is the 64th. If I plug in a -1, it flips it, so I get 4. And if I plug in a -2, it flips it and squares it. So 4 squared is 16. All right, let's see what that looks like when we graph it. When I plugged in a 0, I got 1. When I plugged in a 1, I got 1/2, 1/8, 1/16. And when I did this here, they got even smaller. Going the other way, when I plugged in a -1, it became 2. Plugged in a -2, it became 4. And this one here, when I plugged in a -1, it became 1/4, and then shot up to 1/16 way up here somewhere. Okay, so those are graphs of your functions. So again, what I want you to realize is when your b is greater than 1, you have exponential growth like this, it goes up. When your b is between 0 and 1, it goes downwards. If you have a negative b, it would be down here in the bottom quadrants. Okay, so just one more. Let's just plug these in real quick. I'm going to plug in 0 for x in here. So 2 to the 0 plus 2 is going to be 2 squared, which is 4. 2 to the 1 plus 2 is going to be 2 to the third power, which is 8. 2 to the 2 plus 2 is 2 to the fourth power, which is 16. What happens if I plug in a -1? 2 to the -1 plus 2 is going to be 2 to the 1 power, which is 2. And if I plug in a -2, 2 plus -2 plus 2, that becomes 2 to the 0 power, which is 1. And just do this one just real quick. 2 to the -3 plus 2 becomes 2 to the -1 power, which flips it. And here's your graph. All right, let's keep going. Uniqueness of b to the x. If you have b to the x equals b to the y, and you have the same values for b, you can cross those b's out, and then you can just say that x equals y. Okay, so why is that important? If you have something like this and we want to solve for x, okay, what I need to do is get our bases the same. So we have the same b. Now, I can rewrite 36 as 6 squared, right? So now this equation looks like 6 to the x equals 6 squared. And since our bases are the same, you can just cancel them out. So x equals 2. Okay, let's try to get the bases the same on this one here. Well, 81 is the same as 9 squared. So I can just say, can't get my pen to work right, 2x plus 1 equals 9 squared. Now that my bases are the same, I can cancel them out, and I can just solve the exponents. So 2x equals 1, and then x equals 1/2. Okay? Okay, what about this one? Let's try to get these bases the same. 1 over 27 is the same as 1 over 3 cubed. And 3 cubed I can move up by saying 3 to the -3 equals 3 to the 2x. So 3 to the -3 is the same as 1 over 27, right? So now I have the bases are the same. So I can say -3 equals 2x. Man, my pen's glitching out. Equals 2x. So that means x equals -3 over 2. Okay. Now the last two problems on here are using these in practical applications where we use exponential decay, and exponential growth, okay? Exponential growth we can use with like a compound interest formula, like this first problem. Now this formula will be given to you. So here's the formula for exponential, this is for compound interest, simple compound interest. And so to calculate it, you have P, which is your principal. It's what you start with, so 5,000. And then we use 1 plus, and then this is representing our interest rate. Our interest rate is 6%, so that's going to be 0.06 is 6%. N represents the number of time it's compounded, so our interest is compounded monthly. That means every month they recalculate it. So monthly means we're doing it 12 times a year, so our N is going to be 12. And then here we're going to take this exponent, n times t. So n is the number of times it's compounded, and t is how many times we're going to do it first. So we're going to do that for 18 years. Okay? So what's so important about that? So this is the total number of times it's going to be compounded, and then this is going to find our interest for us. So if I replace these values, I get A equals 5,000. 1 plus, okay, our rate was 0.06. We're going to compound that, 12 times per year. And we're going to set the exponent at 12 times another number of years, 18. And then we're going to plug that into our calculator. Okay? To type that into your calculator, okay, let me get my calculator out. All right, we're going to type in 5,000 parentheses 1 plus parentheses 0.06 divided by 12. Okay, and then we're going to raise that to the parentheses 12 times 18. Okay, and so this tells us that after 18 years we are going to have $14,683.83 left in our bank account. $14,683.83. Okay. All right, let's keep going. Almost done here. Here we have an accidental spill of 100 grams of radioactive material in a local stream has led to the presence of radioactive debris decaying at a rate of 5% each day. Find out how many debris still remain. Okay, so the formula for that we're going to use for this is this problem here. And this 2.7 is it represents the half-life, I guess, for this material. Okay, and so we're going to start with the amount of radioactive material. So how much do we have in here to start? Well, we have 100 grams. Okay, this 2.7 is going to stay. And then this is to a negative exponent, which means we're going to have a decay problem, so it's going to go downwards. So over time, there's less and less of this radioactive debris in there. Okay, and so we're going to put R is going to be our rate of decay. So it decreases 0.05% per day. And then we want to figure out how much is going to be in there after 30 days. Okay, so T is the number of days. Okay, so we're going to rewrite this equation. Y equals 100, 2.7 to the negative 0.05 times 30. Okay. All right, so let's plug that into our calculator. 100 parentheses 2.7. Hi, I'm almost done. I'm almost done. To the parentheses negative 0.05 times 30. And boom. Oh, shoot. Let's see. Go to, where's my error? Is that negative? There we go. All right, try that again. And there we go. So that's how much is going to be left inside. There's going to be, in the stream, there's going to be 20